Hello, algebra students, and welcome to video 1 for lesson 3.3 on transforming linear functions. This idea of transforming or transformations is a theme in math. We'll definitely do this throughout the year in algebra. You'll do transformations in geometry, more geometrically speaking, but you still will. And then in algebra 2 and pre-calc, definitely. If you all have to take algebra 2, but if you get to pre-calc, transformations is key. So it's going to be a little bit of a notation kind of section. So again, don't get lost in the variables and all the different letters. Just try to think it through. Okay? All right, good deal. All right, so first here, vertical translations of linear functions is the positions of two baby sea turtles making their way to the water after hatching from their eggs is recorded. They move at the same speed, with Byron starting 2 feet ahead of Frank's starting point. So same speed, Byron is 2 feet ahead of Frank. So that means be the two turtles, Byron and Frank. What function represents each turtle's position as they make their way to shore, right? And again, this keyword of functions, that's what we're talking about here, linear functions, this entire topic. So from last lesson, you should know that the function notation for a linear function is f of x equals mx plus b, right? Slope-intercept form with y replaced by f of x. So we need the slope and the y-intercepts. Well, the y-intercepts are here on the y-axis. So we know one of them is 2, that's for Byron, and then one of them is 0, and that's for Frank. But now we need the slopes. Now because they're going at the same speed, the slopes will be the same. So let's look at Byron's graph. If I start at this point here and I go up 1, so up 1, and I go right 1, that would be my slope. So my slope here for both of them is up 1 and right 1. That would just be a slope of 1, and that would be feet per second. Feet is your unit of distance, and if you look down here, seconds is your unit of time. So now I can fill in. So for Frank's formula, let's do f of x for Frank. F of x equals, well, his slope is 1x. Plus, and his b value, his starting point is 0. That translates into f of x equals x. You don't need the 1 in front of the x. You don't need the plus 0 afterwards. So there is Frank's function. Byron, let's call him g of x. So g of x equals, again, he's still going at a speed of 1, so 1x. And now we're going to add 2 because his y-intercept is 2. So his formula is g of x equals x plus 2. So you can see that because Byron is 2 feet ahead, right? He has a y-intercept of plus 2. Notice how the red graph, how Byron's graph, compares to Frank's graph. Everything is moved up 2, up 2, up 2, right? Every point is moved up 2. So that is what they mean by this vertical translation, and I think we'll talk about it more on the next screen. All right, so here we go. So I got ahead of myself. Okay, so what happens to the graph of the function when you add a constant? When you add a constant to its output, right? So this is the idea. What happens when you take something and add a constant to its output? Now we've got to remember a constant is just a number. A constant is just equal to a number, okay? So the two equations from our last problem are right here. Right? G of x equals x plus 2, and f of x equals x. So when we're adding a constant to its output, that means we're adding a constant to the y. Right? Well, the y, when you add something, is going to go up. And this is the comparison we talked about in the last problem, which is this problem just rewritten. The red graph, Byron's path, was up 2 from every spot on Frank's graph. And that is because of this plus 2 added after the x. So what you're doing is you're plugging in x into the function, and then for the red graph, you're adding 2 to its y every time. This is going to translate into a graph up 2 units. So again, this plus 2 after it is going to move the graph up 2 units. And again, if you look here, this was the f of x graph, and this, of course, is the g of x because all of its points are up 2. This is an important idea. This is your vertical translation idea. All right, so let's generalize it right here. Okay, so a transformation of a function f maps each point on its graph to a new location. So that's what a transformation is, just a movement, right? So one type is called a translation. That's what we just talked about. A translation shifts each point of the graph the same distance. So translation, right? That's what we're doing here, translation. And it may be horizontal or vertical. So here, they're expressing a vertical translation. So in this vertical translation, all of G's points are up 2 compared to, actually they're up 4 because of the way they're counting, up 4. And over here, this is a horizontal translation. So for the red line G, all of its points are 1, 2, 3, 4 units to the left. Okay? So again, a vertical translation and a horizontal translation. All right, so here, let's really talk about this idea. Okay, horizontal translation now. How does adding a constant k to the input of a linear function affect its graph? So now, instead of adding a k to the outside, we're going to now add a k to the input. And again, we should know that our input is the x. Okay? So here are two functions to consider. F of x equals 2x minus 4, and then g of x is 2 times x plus 5 minus 4. This is the constant we're adding to the input. We're adding it to the x first, and then doing the rest of the stuff. Then doing the 2 times, then doing the minus 4. Okay? But the plus 5 gets added first. So the question is, what is this plus 5 going to do? Well, I assume it's going to be a movement of 5 somewhere, but I don't know quite where. Well, let's just make an input-output table for our functions. So we're going to put an x column, an f of x column, and a g of x column. Okay, so let's start at -2. Let's plug in -2 into our function f. So I'll do it right here. So f of -2 equals 2 times -2 minus 4. Right, I just took this function and I replaced -2 in it. And we're going to simplify this, and this will simplify to -8. So that is a point on f's graph. -2, 1, 2 to the left, -8, 1, 2, 3, 4, 5, 6, 7, 8. Right there, I think. 6, 7. Good. Okay. And I'm going to keep going. So let's do -1. So if I plugged in -1 in for x, 2 times -1, so I'll do it right here, 2 times -1 minus 4. That's -2 minus 4 is -6. Plug in 0. 0 takes away the x term, you get -4. And maybe you can see the pattern, right? If I plug in 1, -8, -6, -4, -2. If I plug in 2, -2, 0. And I got to go one more to prove a point. So I'm going to go 3. Typically, I would stop at -2 to 2, but I'm going to go one more, and that would be 2. Again, you're just adding 2 each time to the f of x. And I'm going to graph these, right? So -2, -8, -1, -6. 0, -4, 1, -2, 2, 0, and 3, 2. And there's my line. I'm going to graph that, and that is your f of x. So that's like what we call, that would be like the parent function, right? That'd be the function without the transformation. And now what is this plus 5 going to do? Let me change colors. So if we plug in now -2 into this one, so now g of -2 equals 2 times -2 plus 5 minus 4. Well, now immediately it's going to take this -2 and make it a value of 3. This simplifies to 3. So when we plug in -2 into g of x, it's like we're plugging in 3 into g of x. All right? So that's really, something to think about, right? Is that's what this plus 5, it's taking our x value and changing it. And now we have to simplify this. 2 times 3 is 6, and 6 minus 4 is 2. So when we plugged -2 into g of x, we got out 2. We got out the y value for f of x when you plugged in 3, when we plugged in -2 into g of x, right? The difference between -2 and 3 is a difference of 5, right? That's that change. Okay? Now, what if I plug in -1? Again, I'm going to add 5 to it right away. So now it's like we're plugging in 4 into g of x, right? 2 times 8 minus 4, that's 4. We plug in 0, I'll get 6, 8, 10, 12. Pattern. And I'll graph these. So negative 2, 2, negative 1, 4, 0, 6, 1, 8, and 2, 10. I can't get to 3, 12 because I go too high. And there I go. And there's this graph. And this is our g of x. So now the question is, what happened, right? How did this 5 affect g of x? Well, if you look, it's horizontally, right? So that means left to right. If you look at this point, again, the negative 2, right? When x is negative 2, right here, negative 2. How does it compare to this point right there? Well, the g of x slid to the left, 1, 2, 3, 4, 5. It went left 5. That is what this plus 5 does. It takes the graph and slides it 5 to the left, opposite of what it looks like, right? We would think plus 5 would mean to the right, but this is actually to the left. So this is a horizontal translation. Horizontal translation. Horizontal translation. And again, g of x is 5 units to the left of f of x. So it's very important that you think about when you do vertical shifts, you go in the same direction. But when you do horizontal shifts, you go opposite of what you think. Okay. All right, great. So thanks for watching this first video. The second video is coming up here next.